Okay, so we're going to do another dot game. So I'm going to draw a Hershey bar over here. Okay, looks like it's working now. And so on your turn, you make a horizontal break or a vertical break. And the last one to make a break wins. And the question is, do you want to go first or second? And so in the previous game, there was clearly a strategy, but it wasn't clear what that strategy was. So over here, for instance, maybe I first make my break all the way down here. And now we have 2 chocolate bars. And then the next person, maybe they choose to make a break over here. And you have to go all the way across. And then on my turn, maybe I'll look at the big board, and I will choose to go all the way across from here. And then maybe the next person goes here. So basically what you're doing is you're filling in all the internal segments. And then maybe I've now got this chocolate bar here, so I'll go here. So you win if you are the last person to move. So if you're the last one to be able to make a break. And so the question is, what is the strategy? And so I think I just moved again, so then the next person can move. Then maybe we'll do some kind of alternation. I'll go here, they'll go here, I'll go here, they'll go here. And you can keep going like this. And so the question is, who has the winning strategy, and what is that winning strategy? And so when I do this in school, what I often do is I have the students play a bunch of games with each other. And I'll have them, maybe it's M by N. And I'll record M, N, and then who won. The first player or the second player. And you'll start gathering data. And then the question is, does sometimes person 1 win on this board, but sometimes person 2? Does person 1 always win? What can you figure out? So I'll leave this just as something to ponder for now. Is there a winning strategy? And if so, what is it? I will give you a hint that there is a winning strategy. And unlike the other game, I can describe the winning strategy in a very elegant manner. Very, very easy to describe what the winning strategy is.
So after the first break?
So the first break I went down here. Yeah. So after the first one, it looked like I now had 2 pieces of chocolate like this.
Yeah.
And then there must be more.
So you don't throw out the first one?
Nope, you don't throw out the first one. And so there's lots of different ways you can play it. So one way you could play it is you throw out the small of the 2. The provost at Williams is an economist. He's my cubby buddy. When my daughter and his son were younger, they had cubbies next to each other in preschool. And so we would see each other all the time. And so we started to try to do some really fun economics variants of this, where there's intertemporal loaning about how much it would cost to, maybe the move is a function of how many squares you block off. And the more things you block off, the more money that costs. And there's a lot of fun tweaks you can do for stuff like this. All right. So that can be pondering in your mind as to what strategy do you want to use. Do you want to go first or second? And does it depend on the dimension of the board? Do you sometimes want to go first and sometimes do you want to go second? In any problem like this, you should always start with small cases and analyze. The 1-by-1 board is not that bad. So then, all right, what do you look at next? You look at maybe the 2-by-1. And then the question is, after that, what do you look at next? Do you look at the 2-by-2, or do you look at the 1-by-3? Do you first try to understand just one row? And the idea is to gather data. And this is a great exercise to do with students. And so I've done it all the way down with 3rd graders this year. And they formed tables, and the 3rd graders found the strategy. But unlike the 5th graders, they hadn't seen me enough. So they're going, oh my God, you moved it. They actually bought that. I don't think I can do it much longer with them, but. OK, so what I wanted to do now is Taylor's theorem, and then after Taylor's theorem, do some examples, and then get into the Fibonacci numbers, and try to connect the sequences in series to understanding the Fibonaccis. So there are a lot of versions of Taylor's theorem. I am going to do the poor mathematician's version, where I'm not going to get the best possible error term. I'm going to just get a decent error term. So the idea is you have some function f, and you want to approximate f, and say, when does f equal the following infinite sum? F of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed, and so on and so on and so on. So the hope is that if you add more and more terms, it will become a better and better approximation. I'm doing this about the point 0. You could do this at other points. It turns out not every function can be approximated well by a Taylor series. And here is probably the best example of a bad function. So let's let g of x be e to the negative 1 over x squared if x does not equal 0, and 0 if x equals 0. This is how many of you have seen Princess Bride? Almost none of my students have seen Princess Bride. So very similar to mostly dead, this is a mostly nice function. Right? There's only one place where this function isn't nice. What's that one place? 0. Yeah, because at 0 I have a split definition. But everywhere else the function is nice. Well, let's look at what happens as x gets very, very close to 0. Well, if x gets really close to 0, let's say x is 1 over 1,000. Then we have e to the negative 1 over 1,000 squared. Well, 1,000 squared is 1,000,000. So this becomes e to the negative 1,000,000. So this is really small. So the smaller x is, the larger 1 over x squared is. This function really decays near 0. So if you were to plot this, the function would look something like this, where it is extremely small near 0. Let's try to approximate it with some kind of series expansion. Let's calculate its derivatives. Well, the place we want the derivatives are at x equals 0. Unfortunately, we have a split definition. If I take the point x equals 5, I can just use the rules of differentiation. Because I'm not at a point like 5, because I'm at 0, I have to go back to the definition of the derivative. So we would get f prime of 0 is the limit as h goes to 0 of f of 0 plus h minus f of 0 over h. So this is the limit as h goes to 0. OK, f of 0 plus h, this is just e to the negative 1 over h squared.
Oh, we're doing g?
We're doing g, sorry. Thank you. So and then these should also be g's. So it'll be e to the negative 1 over h squared minus 0 over h. OK? And so now the question is, how would you evaluate this limit? What does the numerator go to? And the denominator. So what rule do we use? So you could use Lhopital. A lot of people don't like how this looks because when we take the derivative again, we're going to have more h's coming down. So let's say that this is the same as the limit as k goes to infinity. And I'm going to let k be 1 over h. So I'll have e to the negative k squared, and then 1 over h is just k. So this is actually the same as the limit as k goes to infinity of k over e to the k squared. This just makes the Lhopitaling, I think that's a word, a little bit easier to do algebraically. Right? Because if I try to do the Lhopital here, the derivative of h is going to be 1, but now when I take this, I'm going to be increasing the denominator. That's not going to be that helpful. But if I let k be 1 over h, well, then the 1 over h just becomes k. This is e to the negative k squared. Well, that means there's just 1 over e to the k squared. And now if I Lhopital it, I get the limit as k goes to infinity. Derivative of k is 1, and the derivative of e to the k squared will be 2k e to the k squared, which goes to 0. So we now know that g prime of 0 is just equal to 0. If you wanted to do g double prime, well, we can differentiate it everywhere, and we can get the value of the derivative everywhere except 0, and you can keep Lhopitaling it. As an exercise, prove every derivative at 0 equals 0. All of the derivatives of this function are 0. So if you want, at time 0, it's 0, its speed is 0, its acceleration is 0, the acceleration of the acceleration is 0, everything is 0. Well, if I now plug this in over here, if I try to do a Taylor series expansion of g, if I try to write g as a sum, I get 0 plus 0 plus 0 plus 0 plus 0. So my approximation is the function is identically 0. This function is not identically 0. It's only 0 at the origin. So the question is, how good of a job did we do? We got the correct value at the origin. This is not anything worth writing home about. Look at the expansion. When you take x equals 0, everything vanishes, but the value of the function is 0. You have to get the value of the function right at 0. You can't help it. So when you ask, how well does the Taylor series converge? Well, it's got to get the value right at the point you start with. You want to know, does it work anyplace else? And the answer is no. For this one function, it only works at this one place. Its radius of convergence is 0. And so it's because functions like this exist that real analysis is such a hard subject. So if people are interested, I will say a little bit afterwards about complex analysis. Complex analysis is the country club of mathematics. And this is not one of the good country clubs. This is one of the exclusive country clubs that are going to be sued because they only let certain functions in. But because they only let certain functions in, if your function is complex differentiable, you are very different than if you're real differentiable. And while this function is real differentiable, if you replace x with z equals x plus iy, where I is the square root of -1, this function is not complex differentiable. And so complex analysis knows that this is a bad function and will not allow it to come into play. It turns out in complex analysis, if you're differentiable once, you are differentiable infinitely often, you have a Taylor series, and you agree with your Taylor series. So complex analysis is very, very nice. Real analysis is not. Here is a function where the radius of convergence is 0. I will give you an example of another really bad function. So when you teach anything in analysis, it's all about counterexamples. You want to have a list of bad functions at your disposal. Here's another bad function. Let's do b of x for bad is x cubed sine of 1 over x. And if you want, I'll say it's 0 when x equals 0. So this function is continuous. If you try to differentiate the function once, it's actually not too bad. You get b prime of x will be, we'll have 3x squared sine 1 over x. And then from the other piece, we'll get we'll have 1 over x becomes a negative 1 over x squared. So we'll have minus x sine of 1 over x and 0. So this function is differentiable once. And if you take the limit as x goes to 0, well, it doesn't matter that sine of 1 over x is wildly oscillating. It's being multiplied by 0, so the function is differentiable. But the function is not differentiable again, because if you try to differentiate again, now when you have the 1 over x squared coming out in front of this, now you'll have sine of 1 over x, and it's going to blow up. So this is only differentiable once. And this is very different than complex analysis. So complex analysis, if you're differentiable once, you're differentiable infinitely many times. So I'll just say one last bit of complex analysis, then we'll go back to Taylor series. How many of you have seen The Karate Kid 2? And you learned the secret of Miyagi karate? Okay, so in real analysis, we've talked a lot today about limits. So I have some point here, and I want to approach this point. How can I approach this point? What are really the only paths I have? Yeah. I can basically go to the right, and I can go to the left. And essentially, that's all we can do. I'm just checking to make sure it's recording. The numbers seem to be moving up good. There's really not much we can do. So when you say a limit exists in real analysis, when you say a limit exists for a function of a real variable, when you say a limit exists in calculus 1, you're basically saying, well, I checked both paths. That's all I have to check. So I talked a few moments ago about my cubby buddy. When my kids were younger, I actually had preschool classes making pictures for my calculus students. And the pictures they got was, here's my point. And I would tell the kids, just draw scribbles that seem to get near the point. And they would draw stuff like this. I hope you don't need this marker again. And if you say the limit exists, it's got to exist along every path, including a path like this. And so for a limit to exist in 2 dimensions, for a limit to exist with x plus I, y, it's far more meaningful than just saying the limit exists in 1 dimension. And it turns out that the consequences of having to exist along all these paths leads to much nicer properties of differentiable functions. So a lot of these bad problems do not exist in complex analysis. So let's go back to Taylor's theorem. So we were hoping that in some situations we can approximate our function like this. And so you might wonder, why do we care about approximating functions like this? What's the motivation to tell students? In the book, that always works for some kids. One idea is, well, functions are typically complicated. Polynomials are typically nice. If I can replace something that's complicated with something that's nice, maybe this will be good enough for practical purposes. What's a practical purpose? Something very similar to this is how we do streaming video. So what I'll do is I'll show you, after we do this, how to do streaming video using Taylor's theorem. Okay? We won't actually use Taylor's theorem. We'll use an analog of Taylor's theorem, but close enough. So this way you can tell your students, why do you care about this? Have you ever watched anything on your computer? Would you like to watch it again? Do you like it when it pauses for large periods of time? Now, unfortunately, technology has gotten a lot better than when it first started to stream and you would have all these pauses. But how do you stream video efficiently? Well, it's basically using stuff like Taylor's theorem. All right. So I'm going to define either TNF at the point x or f sub n of x to be a Taylor approximation of degree n by just taking up to the first n derivatives. So it'll be f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared plus dot 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 plus the nth derivative, and we put the n in parentheses like this, at 0 over n factorial x to the n. And the idea is that this should do a good job of approximating the function. So as an exercise, show that f n at 0 equals f of 0, f n prime at 0 equals f prime of 0, all the way up to the nth derivative at 0 is of the Taylor approximation is the nth derivative of the original function at 0. And so what we're basically saying is, let's match the initial location, let's match the initial speed, let's match the initial acceleration, and then that should do a pretty good job of approximating how things vary. To see this, if you just keep taking the derivatives, if I take n derivatives, the only term that's going to survive is the x to the n. I'm going to have n minus 1, so an n factorial is going to come down and cancel that. And so when I take n derivatives, I'm left with the nth derivative at 0. Imagine I take n minus 1 derivatives. Then the second to last term will survive, and the last term will survive. The second to last term, I would have, f n minus 1 of 0 over n minus 1 factorial. And then I have an x to the n minus 1. So that would give me an n minus 1 factorial. And then I would have an fn at 0 over n factorial, n minus 1 factorial x. And then all the stuff before that would be 0. And so now when I put in x equals 0, this will vanish. The n minus 1 factorials cancel, and I'll get the n minus first derivative at 0. And so if you just keep repeating like this, you'll see that the first n derivatives all match up. If you think about it, imagine at time 0, you know you're 5 miles from home. Where do you think you are 1 minute later? What's your best guess?
Walking or driving?
Either. You start off 5 miles from home at time 0. What's your best guess for where you are 1 minute later? 5 miles from home. Why is that your best guess?
Only thing I know.
It's the only thing you know. Well, it's the only thing you know about this problem, hopefully.
Yeah.
Right? We don't know which direction we're traveling. So, right? So I don't know, are we getting closer to home? Are we getting further from home? What if I now tell you that at time 0, we're 5 miles from home, and we're going away from home at 2 miles a minute? So we start, f of 0 is 5, and f prime of 0 is 2 miles per minute. I will not say whether or not this is a reasonable speed, but what's your best guess now for where we are 1 minute later? 7 miles from home. So you would then guess maybe f of 1. Best guess is probably 7. And what you're doing is you're doing a linear approximation. We're assuming that my speed stays constant at 2 miles per minute for all eternity. Not a good assumption. For small amounts of time, though, it should be a good assumption. And so the smaller x is, the more important the linear term is over the quadratic term, and the more important the quadratic term is over the cubic term. So for small times, it should be a really good approximation. And the key word is should. That's why I wanted to start with this really bad function g of x, where the Taylor series is never going to be right, but it will be extremely close, because the function is so close to 0. Okay. So the question becomes, how good of an approximation is this? So what can you say about the error? So the error is going to be f of x minus fn of x. And the hope is that this is small, and that maybe the larger n is, the better. So if f is n plus 1 times differentiable, then we get that the error at x is less than or equal to the maximum I'll do x tilde less than or equal to x of f of x tilde in absolute value. I'm sorry, the n plus first derivative. Right out the most base. The n plus first derivative at some point in my interval times x to the n plus 1 divided by n plus 1 factorial. So when you look at this, there's 3 sources for the error. There's the maximum value of the n plus first derivative. There's the x to the n plus 1. And then there's the n plus 1 factorial. So later today, we'll actually see how fast n plus 1 factorial grows. Can anybody give me a physical interpretation of what 4 factorial means? So it's the number of ways to arrange 4 objects. 2 factorial, number of ways to arrange 2 objects. Later today, I will prove to you that negative 1/2 factorial, the number of ways to arrange negative half of an object, is the square root of pi. But there's going to be pizza later? Yeah. So but it'll be the mathematical pi, but not the pizza pi. I will show that the number of ways of arranging negative 1/2 of a person. Okay. So n plus 1 factorial. This is actually going very quickly. But n is fixed, and because n is fixed, if you make x smaller and smaller and smaller, the x to the n plus 1, you can make that much smaller than the n plus 1 factorial. This is just a fixed number for a fixed value of n. It's nice to have it there, because that means your error is going to be smaller. But the real thing is, as I make x smaller and smaller and smaller, well, that just makes the maximum value. It can't get larger. That's good. And I start to gain real savings from here. So if I decrease x by a factor of 10, I decrease my error by at least a factor of 1 over 10 to the n plus 1. That's great. So if you take x to be really, really small, this error is not going to be that bad. What I'm going to do is I'm going to prove Taylor's formula, but I'm not going to include the n plus 1 factorial in the bottom. A lot of the calculus books have proofs of this. If you go to Wikipedia, if you Google, they have the proof as well. I don't like the proof as much with the n plus 1 factorial. I find it a little bit harder to follow, and there's a little bit more of this divine inspiration as to what you're doing. I like the more concrete, roll up the sleeves, see what I'm doing. So I will do it without this. So I will put this in special blue. I am not going to do that. OK. All right, so let's go through and let's do the proof. So proof of weaker claim. So let's let E of x be f of x minus fn of x. So we're looking at the error. There is one place where the error is extremely easy to estimate. Where is that place?
At the end of the whole series.
I'm sorry?
At the end of the whole series, it's 0.
What do you mean by it's
You
0?
wrote out all the infinite number of terms.
Well, no, but not necessarily, because remember, I start off with that terrible function g of x, where the infinite sum does not.
Okay.
And that's why I started with that function. So for a fixed value of n, there's one choice of x where it's very easy to estimate the error. 0. And we know e of 0 is 0. That's just for myself for later. And that's an r, not a k. Okay, so we know that the error is 0 at 0. Any thoughts as to what theorem we should use? Yeah, why not? Let's use the mean value theorem. It's been almost half an hour without using the mean value theorem, right? So e of x is the same as e of x minus e of 0. And by the mean value theorem, this will be e prime at some point c, and I'll call it c1 times x. Okay. The blue seems to be having a little bit of trouble, so I'm going to shift to black. Okay?
Sorry.
Yep.
I get it.
Yep. So this is just mean value theorem.
Because that's already 0.
That's already 0, right? And that's the whole point, is because this is 0, we can do this. Okay, so now that we know that this is 0, what is e prime of x? Well, if e of x is f of x minus fn of x, e prime of x is f prime of x minus, now I've got to take the derivative of the Taylor polynomial. So the derivative of f of 0, well, that just goes away. F prime of 0 times x is just f prime of 0. Then the next one will be f double prime of 0 over 2 factorial times 2x. New blues are coming? Excellent. So we'll then...
I don't want to be in the middle.
This is your chance to star. So we'll now have f prime of 0 plus f double prime of 0 over 1 factorial times x plus dot 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 plus the nth derivative at 0. And then I'll have an n minus 1 factorial x to the n minus 1, because I've taken one derivative. Okay? So I've just taken one derivative of the Taylor polynomial. What is the one point where it's easy to evaluate e prime of x? 0. What's e prime of 0? It's just 0, right? We've said that all the derivatives match. So when I take x equals 0, all of this vanishes and I get f prime of 0 minus f of 0. So note e prime of 0 equals 0. So if I want to understand e prime at the point c1, note e prime of c1 is just e prime of c1 minus e prime of 0. How should we understand e prime of c1 minus e prime of 0? Mean value theorem, right? When in doubt, just keep using the mean value theorem, right? So that'll be e double prime at some point c2 by the mean value theorem. So this is why I really like this proof, because I keep doing the same thing again and again. I keep using the mean value theorem. We've proven the mean value theorem. I understand the mean value theorem. And the mean value theorem is particularly nice if the initial point is 0. And so now, let's collect everything we have. So we get the total error, e of x, was just e prime at c1 times x. Oh, but now this is e prime at c2 times c1, right? And c1 is really c1 minus 0 if you want to be extremely pedantic. And so then I get the error at x is the error derivative at c1 times x. But now by plugging this in, this is the same as the error 2 derivatives at c2. times c1 times x. And this is where you now wave your hands and say, arguing like this, we would also get that this would be the same as 3 derivatives at some point c3 times c2 c1 times x. And then you keep going. And eventually we would have the n plus first derivative at some point c n plus 1, c n minus 1, c2 c1 times x. Well, now, if I take the n plus first derivative, this was a polynomial of degree n. So when I take n plus 1 derivatives, n plus 1 derivatives of fn of x is just 0. So n plus 1 derivatives is just going to be f of x differentiated n plus 1 times. So this will just be the n plus first derivative of f evaluated at some special point cn plus 1 times cn minus 1, c2, c1 times x. I'm assuming, maybe that x is positive. If it's negative, you can do it the same way. Here's 0. Here's x. There's some point c1. And then c2 would be somewhere between 0 and c1. Then c3, maybe c3 is actually equal to c2 as well. And then maybe c4 is over here. All of these values here are at most x. So we get that the absolute value of the error is thus equal to the maximum value of the n plus first derivative at some special point. I'll just call that point c, times absolute value of x to the n plus 1. And that's because all of these c's have to be less than x. So this is almost the full strength of Taylor's theorem. The only thing we don't have is we don't have the extra n plus 1 factorial down below. It's nice to have that n plus 1 factorial. It grows really rapidly. But this is, I think, a much easier proof, and I think it's a more intuitive proof as to what's going on. I start off by how far apart am I? And because the endpoint is 0, I can just use the mean value theorem. And since we've already used the mean value theorem for the fundamental theorem of calculus, it's something that's on people's radar screens. Any questions about this? Okay, so now I want to talk about streaming video. Let's do an application as to why would you care about these approximations. So what we're doing here is we're transmitting something in terms of a basis. So we're trying to expand our function in terms of how much of this function is in the one direction, how much is in the x direction, how much is in the x squared direction, how much is in the x cubed direction. You can choose other bases. And you might have heard about Fourier series with sines and cosines. You might have heard about wavelets. Depending on what you're looking at, different bases are better. Let's just do the standard stuff over here. Imagine you want to transmit a function. Right? So here's my function. Here's 0. Here's 1. How would you send this signal to somebody? So there's a couple of ways you can transmit this. What's one way you could transmit information like this to somebody? Any thoughts? Or? But how would you physically transmit that? So okay, so what you might do is you might choose, let's choose a bunch of points down here, and for each of these points, we'll transmit the value of the function. And that'll be a good approximation. And the more points I take, the better approximation it will get. Otherwise it's choppy. And then unfortunately, maybe the function has a couple of places where it varies really wildly. And if your separation is too large, you'll miss that. So the more points you transmit, the better you'll do. The problem is that it's expensive to transmit points. So the idea is rather than transmitting the values of the function, so method 1 is you send a chain, x1, f of x1, x2, f of x2. You send a collection of points. The other thing you can do is you could send the first few Taylor coefficients. And then you could use that to build up the function. So it's important to really think about what's going on. My phone is charging because it is an old phone. It's almost as old as my daughter, who's in 3rd grade. There's probably more computing power in that phone than in the Voyager space probes from the 1970s. So if you're looking for a really fascinating science thing to watch, there's this thing that's called the Grand Tour, where every few hundred years the outer planets line up in such a way that if you launch in a very small window of time from the Earth, you can actually have one probe visit all of them. And with budget cuts, it's nice to be able to get one probe to do all of them. The problem was when that window was going to arrive, we didn't quite have the technology yet to build the probe we wanted. So we launched the best thing we could and tried to upgrade as it was going and just have it rewrite its software. It was absolutely amazing. They did the best they could, and they just tried to improve it as it was going. I think there's more computing power in a smartphone than in the Voyager spacecraft. It's incredible. When you're transmitting information, you're not just transmitting information to some printed medium. You're transmitting information to something with significant processing power. A laptop computer, a desktop, a smartphone, a tablet, something like that. And so it's not that bad for the computer to take these numbers, these Fourier coefficients, and build back your function. And so all you need to do is if you just transmit a couple of these, it will then get you a really good approximation to the function. So how does this then relate to streaming video? Well, you want to transmit images. So, one way to transmit images is, I pixelate things. And so each pixel, I can represent it as a triple of its red, green, blue values. And frequently you might do these between 0 and 255, or if you have worse resolution, maybe between 0 and 15, something like that. And I essentially just need the value of each of these pixels. So what I really want is I have 3 functions. And streaming video is not exactly like this. This is a close enough approximation to what's going on that it can give the sense to the students as to what's happening. I want to transmit 3 functions. I want, if I had red markers here, I'd do my f of r for red. It's OK. F of b for blue. And then f of g for green. OK. And so it's not easy being green. OK, so we have the red, the blue, the green. So now I want to transmit a 2-dimensional, essentially, Fourier series. So I would have my red function would be a function of x and y. And now what I would want is I would want a 2-dimensional Taylor series. And so this is now a multiviewable calculus is beginning to emerge. So we'd have some kind of double sum. And now the notation would be, I'll do it as m plus n of f dxm dyn. So I'm taking the mth derivative of f with respect to x, and then the nth derivative of f with respect to y, evaluate this at points, blah, 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 blah. I'm not going to go into the details of what the multivariable series is. Just this something like this. Or if you want a nicer way of doing it is, screw that. Let's just write it as it's a sum. M goes from 0 to infinity. Sum n goes from 0 to infinity of a, m, n, x to the m, y to the n. And these are my coefficients. And then I can say, well, you know what? If the world is nice, maybe I could approximate these by going up to some big number b. And then all I have to do is transmit these numbers over here, and I can build things up. I mean, I can incorporate the 2 factorial into there if I want to. I don't have to figure out what the coefficients are there. Let's just transmit the numbers a, m, n. And the idea is by just transmitting these numbers, then on the other end, the computer can build them. Then you can ask all these different questions as to what's the best way to transmit. What do you want to transmit? So sometimes people, I think, look at the difference between 2 consecutive frames, because very often there's very little movement that's going on. If you look at the old cartoons, The old cartoons are great where you basically have a fixed background and then you have a very small amount of animation that's happening just because of how expensive things used to be. But this is one of my favorite applications of Taylor series and stuff like that. You can use better things than Taylor series, but that's just earning your highest salary. The principle is the same. You take a complicated function and you build it as a combination of simple ones. And the hope is that enough of these will give you a really good approximation. Someone told me recently that vinyl records are making a comeback. Okay. But I guess the rest of the world has now learned your husband is correct. So is there anybody here who has a really good music ear and can hear the difference between, say, a vinyl record or a CD? Can your husband hear the difference?
That's a good question. I don't know.
Because yeah.
Probably if you kept all the good ones. I don't know.
Well, sometimes it's well, I'll be very careful.
Just the collector's thing.
Right. But so, I've heard that there are some people who can hear a difference. But at a certain point, it's going to be a close enough approximation that for humans, we will not hear the difference. And the question is just, how far do you have to go? And for some of us, it doesn't have to be that far. Okay, so this is a fun application of Taylor series, stuff like this. The idea here is we have a bunch of local information. And we're building this global object, the function f. So this is going to be one of the themes for today. It's local to global. Okay? So you start off with small bits of information, bundle them together, and then somehow you use that to attack the problem you care about. And so one of my favorite applications of this is the Fibonacci numbers. So I don't think we did Fibonacci last time. How many of you have done Fibonacci numbers? How many of you do Fibonacci numbers with your students? Okay. Do you know Benet's formula for the nth Fibonacci number? Good. This is one of my favorite formulas in mathematics. So Fibonacci's. There's at least 3 slightly different definitions of the Fibonacci numbers, depending on what you want to do. I will start with one definition, and so as not to discriminate, by the end I will move to another definition. So I will define them as follows. Fn plus 1 is Fn plus Fn minus 1, and I need 2 initial conditions. F of 0 is 0, F of 1 is 1. And so each term is the sum of the previous 2. As soon as I give you any 2 terms, everything is uniquely determined. So 0, 1, 1, 2, 3, 5, 8, 13, 21, Big Papi, 55, et cetera, et cetera, et cetera. Okay. If you want to find the 100th Fibonacci number, in principle is this hard to find the 100th Fibonacci? No, it's just a bunch of additions. In practice, it's not pleasant. So you can write a computer program. Now the numbers are going to get very large very fast. My daughter was doing a swimming fundraiser, and I told her I will sponsor you at a Fibonacci rate. So if you do 10 laps, I will give you $1. If you do another 10 laps, I will give you net $1. If you do 30 laps, I will give you $2. If you do 40 laps, I will give you. So she had a real incentive because it starts to really, really grow. Okay? So how? She was 115. So, yes, it was. It's a good program. We like them. But if it got up to 120, that would be. But how do you find the 100th Fibonacci? Can you just jump to it? Or what if you want the billionth Fibonacci? To add all the billions would be hard. So there is a closed form expression for the nth Fibonacci. The nth Fibonacci is 1 over the square root of 5, 1 plus root 5 over 2 to the n, minus 1 over the square root of 5, 1 minus the square root of 5 over 2 to the n. So this is Benet's formula. And is one of my absolute favorite formulas in mathematics. The way I like to describe this is, my brother used to say that you should be able to identify your calculus professor in a police lineup. That's the bastard who's been... I've actually had students who could not pass this test. Is they had never been to class, and I was just, the leader, and said, okay, well, who's your section teacher? I don't know his name. What do they look like? I don't know. What can you tell me about Fibonacci's? When you look at the sequence of numbers, what do you think? What type of numbers are they? They're integers. Does this look like an integer? If you were doing a police lineup. No. Yeah, I know it was one of the Fibonacci's that did this to me. It was from the Fibonacci gang. And you bring in this as one of your suspects. You've got divisions by square root of 5. You've got 2. So as a nice exercise, what can you replace the 5 and the 2 by and still always have an integer? What variation? So whenever possible, when you're giving problems to students, see if there's something that they can do which would be new. And it doesn't matter if somebody else has done it. It's new to them. What kind of freedom do you have? What's the relationships between 5 and 2? 5 is 2 squared plus 1. Does that matter somehow? What matters? With the small number of data points, it's not clear. So how can you modify this? So I'm going to give you several proofs of Binet's formula. The first is my favorite proof. It's the method of divine inspiration. Now, what was interesting is I was recently being interviewed for something, and there were all these representatives from a department, but they had a representative from diversity and inclusion who was from the religion department. And they'd never heard of the method of divine inspiration. And I thought it was fascinating that the mathematicians had this method, but the religious people did not. So the way the method of divine inspiration works, goatee or beard is really helpful. You go like this for a little bit, and go, ah! And then you write down the answer, and then you show that it works. So I claim that this is the formula for the nth Fibonacci number. All we have to do is check. So if you put in 0, well, we get 1 over root 5 minus 1 over square root of 5, which is 0. Good. Now we check F1. When we put in 1, we get 1 plus root 5 over 2 minus 1 minus root 5. So the 1 and the 1 cancel. The root 5 and the minus root 5 reinforce to get you 2 root 5 over 2, which is root 5 divided by root 5 is 1. So you get 1 over root 5, 1 plus root 5 over 2 minus 1 over root 5, 1 minus root 5 over 2 equals 1. Almost. All we have to do now is we show that this sequence of numbers satisfies the recursion. If it satisfies the same recursion, then it has to be the Fibonacci's. So now all you need to do is take this at n plus 1, subtract the value at n, subtract the value at n minus 1, and show that you get 0. So I will leave that as an exercise to either you or your students. That's a proof. At the end of the day, it's not a good proof, right? I have no idea how to do this for something else, right? And I have no idea why it's true. So a lot of times you only need the result. So I've got the result. And this is a very useful result. It allows me to jump to the billionth Fibonacci number if I want to. And there are actually times in my life where I want to. But I have no idea how to do something similar. What if I change it to fn plus twice fn minus 1? How would these numbers change? No idea. Well, I know other ways, and then I can just hide that work and be divinely inspired again. But then what if you need to do something new? It's very hard to be divinely inspired. So what I want to do is I want to show you 2 other ways to get to this formula. And these ways will allow us to handle a variety of problems. And so this can be used for mathematical modeling. Any fans of Star Trek 4? The Voyage Home, the one with the whales? So this will help us figure out if the whale population will be saved. So the first idea is to try to get a sense of what's going on. So we have fn plus 1 equals fn plus fn minus 1. So Jill was asking me earlier, what skills do I wish students would have when they come to college? One is an understanding of algebra. Is to be able to look at, I think I heard a chortle, but yes. This is the universal plea, is students cannot manipulate expressions. They do not understand how to simplify things. They don't understand what things are. The other is to have some idea of approximately what should the answer be. So I'll give you an example. This is one of my favorite problems. There's a horrible exam, and I know this is being recorded, called the GRE Math Subject Exam by Education Testing Services. Imagine I can paint a house in 2 days, and my father can paint a house in 3 days. How long does it take both of us to paint a house? Well, I can do, me is 2 days. My dad is 3 days. What can you tell me about us together? Give me some bounds. Less than 2 days. Why less than 2 days?
If dad helps a little bit.
Good. So it's got to be less than 2 days because my dad is not completely useless. I understand this is being recorded. We can do a little bit better, though, than less than 2 days. So it's definitely less than 2 days.
Less than 2.5. Less than 1.5.
Less than 1.5, because if it was 2 of my dad's, and then on the other side, it's got to take at least how long? And actually, it would be a strict inequality because I'm better than my dad. It's better than a day, more than a day. So we know the answer is somewhere between 1 day and 1.5 days. So on multiple choice exams, there will often be only one answer that's in this range. So a lot of students will make the mistake of actually solving the problem because they know how to solve it. Whereas in a multiple choice exam that's timed, you just need to very quickly see what's the only thing in the right range. This is a very useful skill to be able to just look at a problem and get a feel for what the answer should be. So over here, are we near a break or? Okay, the just perfect. Okay. 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 So we know Fn equals Fn plus Fn minus 1. The sequence is increasing. So if you want, maybe we'll just start, 1, 2, 3. We won't start with a 0 and the 1. It's getting larger. So because of this, I claim the following is true. 2Fn minus 1 should be less than equal to Fn plus 1, which should be less than equal to twice Fn. Because if I replace Fn minus 1 with Fn, I can't be getting smaller. And if I replace Fn with Fn minus 1, I can't be getting larger. So do you agree that Fn plus 1 is not larger than twice Fn? So what this means is every time I increase n by 1, I at most double. So this essentially gives me Fn should be growing slower than 2 to the n. I might be off a little bit by how many terms I have in the beginning, but every time I increase n by 1, I at most double. So if you want it to be really accurate, it's less than equal to some constant number times 2 to the n. Because every time I increase n by 1, I at most double. Let's look in the other direction. Here I increase my index by 2. And I've increased by a factor of 2. Fn plus 1 is at least twice Fn minus 1. So every 2 times, so it's going to be a square root of 2. So I'll call this C upper, and I'll call it C lower, square root of 2 to the n. Or if you want another way of looking at it is, it's 2 to the n halves. Every time I increase n by 2, I get an extra factor of 2. So the growth rate of the Fibonacci's, it's not faster than 2 to the n, and it's not slower than the square root of 2 to the n. So we know maybe the Fibonacci numbers grow like r to the n for some special value of r. So in some sense, I'm doing a divine inspiration now. I'm guessing that the growth rate is like r to the n. But I'm trying to at least justify why I would think this. And it comes down to trying to get a sense of what is the growth rate. Well, if I take Fn to be Fn minus 1, I can't make things larger. If I take Fn minus 1 to Fn, I can't make things smaller. And so because both extremes have exponential growth, it's not unreasonable to assume, well, there's got to be some type of exponential growth. So I'm going to guess Fn is r to the n. So this was the motivation. Okay? So now that we have this, let's just guess that. So we'll guess that Fn is r to the n. So we'll get r to the n plus, r to the n plus 1 is r to the n plus r to the n minus 1. It's fun saying this in Boston. Okay? So I can subtract, I'll get r to the n minus 1, r squared minus r minus 1 equals 0. So I get r equals 0, which is really boring. It's the sequence of all zeros. So I'm not even going to worry about that. So I get r squared minus r minus 1 equals 0. So the quadratic formula tells us r equals 1 plus or minus the square root of 5 over 2. And that's where the golden mean comes from. And now what's fascinating is if I guessed r to the n, what if I guessed 3 times r to the n? Well, I would just multiply every term by 3. It's still a solution. So because this is linear, sums of solutions are solutions. So as a check, if r1 to the n and r2 to the n work, so does c1 r1 to the n plus c2 r2 to the n. And you can just go through, well, if I have 2 solutions that work, r1 to the n and r2 to the n, each one satisfies it separately, I just group the algebra. So it's a nice exercise, just go through, group the algebra. And now we get that the nth Fibonacci number is just c1, 1 plus root 5 over 2 to the n, plus c2, 1 minus root 5 over 2 to the n. And what's nice about that is we're almost home. All we have to do now is find c1 and c2. How do we find c1 and c2? Well, we just plug in certain values. We know f0 equals 0, f1 equals 1. We now have 2 equations, 2 unknowns. And because they're linear equations for c1 and c2, it's not that bad to solve. And then when you do the algebra, you'll get 1 over root 5 and negative 1 over root 5. So this method works for a whole slew of equations like this. What you need is the equations to be nice. So it's got to be a fixed depth. I only have 2 terms here. If the number of terms depended on n, it would be a lot harder. I can have any constants in front of these and it would be fine. If I had things that depended on n, it would be a lot harder. These are called difference equations.
Sorry, the line after guess, can you explain that one more time?
The line after. So I'm guessing fn is r to the n.
Yep,
So now if fn is r to the n,
I got it, sorry.
yep, no problem. So difference equations are discrete versions of differential equations. So basically, you have a discrete step in time. For a lot of processes, it's nice to do this, but then you lose, of course, a lot of calculus. Yes?
Can we talk about the line, the guess line?
Sure. So I was trying to motivate why we would make this guess when we were saying, look, it's growing slower than 2 to the n, and it's growing faster than root 2 to the n.
Yeah.
So maybe it's growing like r to the n for some r.
Okay, so it just happens to work out that it does.
It just happens to work out that it does. But it's not what I'm hoping that you'll believe.
Not unreasonable.
It's not an unreasonable guess, right? But it was still a guess. But it was a guess that we could then put in, and then we could see, does the guess work? And it turns out the guess is not perfect, because it actually could have multiple terms. Maybe the main term is growing like 1 plus root 5 over 2 to the n, but then there's a second smaller term, which is in fact what happens. Now what's really interesting is, does anybody know approximately how big is 1 minus root 5 over 2? Okay, that's all I need. It's point something. So it's actually a negative number, and it's less than 1 in absolute value. So because this is less than 1 in absolute value, as n gets very, very large, this is going to 0. What this is telling you is the nth Fibonacci number is approximately 1 over root 5 golden mean to the n. But we know that the Fibonacci numbers are integers. So all you have to do is calculate for a large number the golden mean to the n, divide by root 5, and take whatever integer is closest to that. And that will be your nth Fibonacci number. Because we know it's an integer, we actually know how to take into account the small effect of this. Okay, so I'll show you applications of difference equations like this a little bit later. I want to show you another proof of the of Benet's formula using what's called generating functions, because it's going to go with the theme for today, this local to global. And we did this with the geometric series. We did this with Taylor series. We take a bunch of local pieces of information, we build them up, and we get a new function. So for the geometric series, we build up 1 plus x squared plus x cubed, and we got this function 1 over 1 minus x. And then we could differentiate term by term, and we got new identities. And the reason it worked is we built it up into a nice function. Then we did the Taylor series. And again, we took all this local information, we built up to a nice function. So now I'm going to show you this with the generating functions. Normally I do this with slides, so I will hopefully try to do this without making any algebra mistakes. But this is one of the big tools in mathematics, this idea of a generating function. Bless you. Okay. So at first, it seems absurd that this could possibly work. So I'm going to define g of x to be the sum, n goes from 0 to infinity, of fn x to the n, or if you want, it's the same as n goes from 1 to infinity of fn x to the n, because we're starting off at 0. So I'm building a function with the objects I wanted to study. So the first question whenever you see a function is, do you converge? Well, we know the Fibonacci's are growing slower than 2 to the n. So if I take x to be less than 1/2, it will converge. So if I take x to be 1/3, it's going to converge. So the series will at least converge if x is sufficiently small. So converges if the absolute value of x is less than 1/2. Okay, good. How can I do anything useful with this? I don't know what the Fibonacci numbers are. And I'm building a function to understand the Fibonacci numbers by putting the Fibonacci numbers in. The reason this is not a completely stupid thing to do is we do understand the Fibonacci numbers. We just don't understand that we know the Fibonacci numbers. Once I tell you the first two Fibonacci's in the relationship, in principle, do you know every Fibonacci number? Yes. In practice, do you know every Fibonacci number? Not even close. But in principle, you do. So let's look and see what's going on. So let's look at the sum, n goes from 2 to infinity, of fn x to the n. And now this is the painful game of playing with indexes of summation. And this is where I would much rather be in the audience. All right, so I'm going to say that this is the same as summing m goes from 0 to infinity. I'm going to write this as f of m plus 2 x to the m plus 2. I'm just shifting my index of summation. Why would I do something like this? I'm doing this because, oh, maybe I want to just shift. I guess I just want to shift it by 1 because I'm trying to match the Fibonacci's here. So I'll go from 1 to infinity. Well, no, I'll go from 2 to infinity, but I'll do it this way. I'll have m goes from 1 to infinity. I'll do f of m plus 1 x to the m plus 1. Because I want to use the Fibonacci relationship here. So this is the same as the sum, m goes from 1 to infinity, of fm plus fm minus 1 x to the m plus 1. This is the same as the sum, m goes from 1 to infinity, of fm x to the m plus 1, plus the sum, m goes from 1 to infinity, of fm minus 1 x to the m plus 1. And this was the sum, n goes from 2 to infinity, of fn xn. Well, this is almost our generating function. Our generating function starts either at 0 or 1. We're starting at 2. So this is just the generating function minus f1 times x. Yes, because we don't have the f1 x term. What about this over here? fm xm plus 1. How should we view this? So it all comes down to, this is the skill we want most. How do you view things algebraically? We want to somehow interpret this in terms of our generating function g of x. We have fm and x to the m plus 1. What would you like to do? Yeah, factor out an x. So this is the same as if I factor out an x, I'll have x, and then I'll have a sum, m goes from 1 to infinity, of fm, xm, and this is just g of x. So this will just be x, g of x. Now what do we do for this one? We pull out an x squared. And so we'll pull out an x squared, and now we'll have a sum, m goes from 1 to infinity, fm minus 1, xm minus 1. Yeah. Right, and so what is this part over here? That's also g of x. It'll be f0 x to the 0 plus f1 x1 plus f2 x2. So we get g of x minus f1x, well, f1 is just 1, so I can just write minus x, is x g of x plus x squared g of x. Okay, what should we do now? I'm sorry? So I'll rewrite it up here. So we now have g of x minus x equals x g of x plus x squared g of x. So what should we do? So what's the algebra I want to do?
G of x over.
Yeah, which g of x over?
So you want them all on.
I want them all on one side. So this is the same as 1 minus x squared g of x equals x, or g of x is x over 1 minus x squared. We actually have a closed form expression for that sum. And this is very similar to the geometric series, where we had a closed form expression. It was 1 over 1 minus x. And because we had a closed form expression for the geometric series, there's a lot we can do. Because we have a closed form expression here, there's a lot we can do. The first thing is, well, let's write this as x over 1 minus, and I'll pull out an x, 1 minus x. And try to expand this using a geometric series, where now my ratio is x times 1 minus x. It turns out this is a horrible thing to do. And the reason it's horrible is because this factor here has one term of size x and one term of size x squared. Oh, this should be a plus sign. So if I try to do this with a geometric series, I'll have x, and then I'll have x times 1 plus x times 1 plus x squared, and then x 1 plus x cubed. So let's say I want to find the x to the 5th term. Oh, crap. A lot of different pieces can contribute an x to the 5th. If I want an x cubed term, this piece will give me an x cubed term. Also, this piece over here, if I take the 1 twice and an x, there'll be an x term. Okay, so if I take 1 once, x once, I guess take x once from here, take x once from there, and then there'll be an x squared times that will be an x cubed. And so I have multiple terms that can give rise to an x cubed. I have multiple terms that can give rise to an x to the 4th. Remember, g of x is just the sum of fn x to the n, and it goes from 0 to infinity. If I can just match and find out what is the x to the 5th term over here, what's its coefficient, I've got a formula for fn. The problem is because these have different degrees, this doesn't work. There is fortunately a solution, and it goes back to something you do when you do integration theory. It is one of the least favorite, if not the least favorite, integration technique. So what do your students hate more than anything else? For a lot of the students, they hate everything. But of all the integration techniques, I usually find that this is the one they hate the most. And any student who doesn't say that this is their least favorite, as soon as I remind them, they'll go, oh yes, I hated that. Partial fractions, right? This is where you use partial fractions. So what we do instead is, this is a bad idea. So gone. We factor 1 minus x squared as 1 minus alpha x, 1 minus beta x. And then we can write this as, we still have our x. And then we'll have a 1 minus alpha x here. We'll have a 1 minus beta x here. We'll have an a here. We'll have a b here. And now we can use the geometric series to expand out each of these. And then what we get is that this is now equal to this, x times the sum, and it goes from 0 to infinity of a alpha to the n x plus the sum, and it goes from 0 to infinity of b beta to the n x. X to the n. And so when we put the pieces together, remember we have the x, we'll have a sum, and it goes from 0 to infinity of a alpha to the n plus b beta to the n, x to the n plus 1. Question? Yep. Sure. So the idea is we use partial fractions here. So we factor the denominator 1 minus x squared as 1 minus alpha x, 1 minus beta x. And so alpha plus beta is equal to 1. And then alpha times beta is equal to negative 1, I think. So you solve those equations. And then, given that we have Benet's formula, I think it's very likely that alpha is, or it used to be here. I think alpha is going to be 1 plus root 5 over 2, and beta is going to be 1 minus root 5 over 2. So if we try alpha equals 1 plus root 5 over 2, and beta equals 1 minus root 5 over 2, what's alpha times beta? I'm sorry, well, let's do the easy one, alpha plus beta. That should just be 1. And if we do alpha times beta, we get 1 plus root 5, 1 minus root 5. That's going to be 1 minus 5, which is negative 4, divided by 2 squared is negative 1. So that's where these numbers come from. They come from partial fractions, and this is another way to get Benet's formula.
So because that's solved by expiration.
Well, this part here?
I mean, there's the finding of alpha and beta.
No. The finding by alpha and beta, you have techniques in partial fractions to solve these.
I've done that in a very long time.
Right. I mean, what I would do here is, if alpha plus beta equals 1, I can solve for beta in terms of alpha. And then this would give us, beta equals 1 minus alpha. And then over here, you would get alpha times 1 minus alpha equals negative 1. So then I would get alpha minus alpha squared equals negative 1, or just rearranging things, I get alpha squared minus alpha minus 1 equals 0. And that's the same equation as we did earlier for the golden mean. And so we can actually find the alpha and the beta. It's just nice quadratics. But in terms of just mathematical enrichment, this is where sequences and series go. Is the whole idea is you try to understand things locally, and you try to come up with some global object that you can build this all together. So we'll do at least one more example of this later today when we do the infinitude of primes. And there's the Riemann zeta function, which is one of the biggest functions in all of math. If you haven't seen it, it's absolutely phenomenal, the information this encodes. And it's the best example of how you start off with ridiculous information, something that's completely trivial, and are able to deduce an enormous amount of stuff in a highly non-trivial way. But it all comes down to the fact that we have a closed form expression for G. If we didn't have this formula here, none of this would work. But because it all comes down to, in a nice way, a simple expression, a ratio of two polynomials, we can do an enormous amount with this. So we can solve a whole variety of recurrence relations. If I gave you something of depth 3, fn plus 1 is fn plus 2fn minus 1 plus 5fn minus 2, we could say, let's just try r to the n again. And this will work in every single time except for one situation where you have to do something a little bit tricky. I don't really want to go into that. I thought I would do an application, and then is that a good time to break?
I just ordered pizza. It should be here between 12 and 10 after 12.
Okay, but it's very easy to lecture. It's not as easy to listen to lectures. So I think after one more. Okay. Well, why don't we stop here? It's much easier to just stop and let things process. So I actually can't turn it off. I have to unplug this.